Extended Access Control List, also known as an extended ACL. The most robust IP filtering mechanism available on the Cisco IOS is the extended ACL. The filtering tool has more capabilities than the Swiss Army knife. At the same time, though, it's very configurable. In fact, it is as easy in some respects as a standard ACL. There's one command used for configuration. In this nugget, we're going to start by defining exactly what an extended ACL is and does. Then we're going to move into a discussion on the configuration. We're going to discuss the fact that there's one command involved in configuration and we make a multi-line text file. After that, we're going to find out how to take that text file and apply it to an interface. We're also going to look at in-depth guidelines for applying ACLs, namely extended ACLs, in a networked environment. Extended access control lists are primarily used as filtering tools, as we see here. These filtering tools can be used now more extensively than the standard access control list was to filter both based on source and destination, and also beyond that to include some protocol numbers and more granular variables within different protocols. As it was with the standard access control list, we do create a multi-line text file, one line at a time with one command issued over and over. The range. This is where we're going to differ from the standard. Here we have the range of 100 through 199, and then we also have the expanded range of 2000 through 2699. The operation of this ACL, as with every ACL, is on a first hit basis. Again, with the multi-line text file, the first line that we match on, let's say it's the second one, we're going to take that action, whether it's a deny or permit, regardless of other matches that take place beyond that line. First hit only, not best fit. Where can they be applied? It can be applied on an interface or a line. Now, when we apply to a line, the functionality remains the same, but the application command is a bit different, and we're going to cover that in another nugget coming up on application on lines for both standard and extended IP ACLs. As with all ACLs, we have an implicit deny all at the end of our list, which exists right here, which says that no matter what these lines above say, if I don't have a match for my packet and I get to this bottom part of the list, I'm going to deny that packet. It will not pass, okay? And it's also used, another usage is to define interesting traffic, as in a crypto map, where we would define what traffic we want to encrypt from one end of a tunnel to another, and also a route map. When you want to define specific routes for traffic, interesting traffic will be identified by the use of an ACL. The use of these two tools within the iOS is beyond the scope of the CCNA, but makes for very interesting reading if you care to do that on your own. All right, next thing we're going to move into is the configuration of an extended ACL. Now, access-list is a part of the command that will always remain the same. You type that in as you see it here. Then we get into the ACL number. Nothing new, same thing as the standard, except now our range is different. 100 to 199, a true 100 different ACLs that we can configure, and the expanded range as well. Then we're going to have an action, a permit or deny, just as we're used to. This is where it gets different. The next thing we're going to configure is a protocol. After that, the second field will be defining the source. Now, there's three ways to do that. You can type in a source IP and then a source wildcard, as we saw with the standard access list. You can type in host with a source IP defined in all 4 octets, so it's a specific source IP, where in this case it could be a network, or it could be any, which is the equivalent of 0.0.0.0 space 255.255.255.255. All right, the third field is going to be the destination. So see, we filter on both the source and the destination, as well as we identify the protocol that we want to filter on. And once we've identified that protocol, depending on which protocol it is, we will have a combination of the operator and the port to define, or just the port. And these are optional. All right, so let's start with number 1. We have the protocols. I'm going to list a few here. There are more than this, okay? But under IP, we have, first of all, OSPF and EIGRP. Both of these are routing protocols that can be used within your backbone. And there may be an instance to where you have 3 routers, let's say, in a routing environment, and you want to block traffic coming from this area here with EIGRP or OSPF traffic coming into this router. You simply place an ACL right here. All right, the next thing is ICMP. ICMP is what is used as a protocol, and it stands behind the ping, the trace route, the redirect messages, and if you'll recall, it's covered in an earlier nugget, all the messages that help you on the backbone of your network to understand a little bit better what's happening in the wire. Okay, other protocols that are available, TCP and UDP. We've got our connection-oriented protocol and our connection-less protocol that are available. Every port within each of those protocols is available. Not just the standard 1 through 1024, but the high order ports as well. And then we have IP as an option, and that encompasses all three of these options. If you choose IP, it includes ICMP, TCP, and UDP for filtering. Keep in mind, these aren't all the protocols that will be available to you, as I said earlier, but these are the most commonly used protocols. In fact, I venture to guess that you will probably not have an access control list without the IP protocol being present in one of the statements. All right, the next portion we need to go to then, now that we've covered the protocol, is the source definition. We have a couple of options, as we had said before, the source IP with a source wildcard. And we're going to see that one right over here, 192.168.5.0. This would be the IP with the wildcard associated 0.0.0.255. What this does is says we're going to filter based on this portion of the address, which is a network, 192.168.5. The way we do that is with the wildcard mask. A brief review, because we covered this in the essentials, is if there's a 0 there, that bit must match exactly. If there's a 1, as in this whole last octet here, it could be anything. So this could be .1 through .254. All right. The other option we have is a host. It's a keyword. You would see that exactly as it's written, like you do here, and then identify 4 octets, 192.168.5.254, an exact IP address of a host. The option to that, if you didn't want to use the keyword host, was here, 192.168.5.254, with the wildcard of 0.0.0.0. This just seemed to be a little bit simpler. Okay, and then the last was the option of any. Again, you can use the keyword any only here, or what is the shortcut for? You can use the long form of 0.0.0.0 and in all 255s in the wildcard mask. I personally would never include this in one of my ACLs, but then again, you know, I don't do some things that others do. Some people like pain. That's how I explain marathon runners. Just kidding. All right. So as you can see, you will probably see this here, or the keyword host, or any in your list, not normally the long forms. Now, as far as source and destination, there really is no difference in how we want to define them. We can use these same keywords to define both areas, 2 and 3, of our command. And then that's going to move us into the optional operators and ports, like I said, that are there dependent on which protocol we chose to activate. Now, because it's dependent on protocol, I'm going to show you, first of all, some of the options with either IP chosen as a protocol, EIGRP, or OSPF, because their options or operators are exactly the same. As luck would have it, the first operator that we're going to encounter is an old friend, and that's the log. This is going to log any matches that occur on a certain line over to the console. Keep in mind that means you have to be connected to the console. So in other words, if you have a router out here attached to a network and you have a PC on that network and you have telnetted across this network into the router, you're not going to see these log messages because they're available to the console on console connections. All right. We also have precedents that we can filter on. Within the IP header, flags are used to establish precedents. And if you knew certain precedences on some packets versus not being present in another, then you could filter on this here. But you know, it's not that often that you're going to see that happen. More often, you'll see somebody filter on type of service. That's what TOS stands for, type of service. And it's not the type of service maybe that you would readily think. It's not a protocol, and it's not a more general type of service. This is actually specifically either normal operation, and this is defined within the header of the IP packet by 4 bits. If all of them are off, you're in normal operation. They also have a minimized delay, and then they have a maximized throughput. Now, while these don't seem too familiar, there is a pattern to them. In other words, certain protocols use each of these, and it may be unbeknownst to us normally, but if you look into it, you could filter using these key fields. In fact, this minimizing of delay is usually present when you are telnetting between devices, or if you have an FTP session set up, or even TFTP. Maximizing throughput is used whenever you have DNS zone transfers between 2 DNS servers. That's UDP. I mean, you can filter that way as well, but just so you know, there's this field as well, the throughput within the type of service being maximized. So let me drive this home and show you exactly how this would be configured. You would see access-list exactly as it's written. You would see an ACL number, maybe 101. You would see an action, let's say this time permit. Then you would see a protocol. at this slide, we're defining the protocols IP, EIGRP, and OSPF along with their operators that are associated with them. So let's say it's IP, and then within the source, you can define any, just to keep it quick on the board here. The destination, let's define any. Here's where we have the optional operators. At this point, you could simply hit return and be done with this line of the configuration in this ACL. Or you could say something like type of service, and then specify minimize delay. And that would be one line within your ACL. TCP and UDP are protocols that are available within the commands as well, and they have different operators. So let's go over them individually. Here we have TCP that we would use in the first field right here, and then we could have any as a source, any as a destination, then our operators. The first that we're going to run into here is acknowledge. This has to do with the three-way handshake in a connection-oriented environment. Let's say that we have one PC here, one PC here. The first thing they're going to do in a three-way handshake is the initiator of the conversation is going to send over what's known as a SYN packet, kind of like saying hello, okay? Then this person in their response is going to send a SYN ACK. You see how the acknowledgement bit is set here on that second packet. If that acknowledgement bit is set, we can filter on it right here. And then that third part of the handshake is simply an acknowledgement. All right, so that's one tool available. Another is equal. EQ is short for equal. And what this means is after the equal operator, we're going to define a port. Let's say 53, which is the DNS port. Equal to 53, we're going to filter on that port. In other words, any match that we have on a packet using this port number will be filtered. Every other port will be left alone. Okay? The next thing we have is the established. This again has to do with a connection-oriented environment. We talked about the three-way handshake that we see here. Once this is completed, we have an established connection. But it goes a little farther than that. Even once that first packet is sent and we have a response here, that can be deemed as established depending on the operation of your device. And with the iOS, this holds true. So if I have established at the end of my access control line, what it means is once that first SYN packet is sent out, that response coming back, I will allow. So how does the iOS differentiate between the packets and where we are within the handshake? I think simply said, it takes this as a rule. If a SYN exists alone, I'm not allowing it to pass through a router. Let's say there's a router here in between these two devices. If the SYN exists alone, it does not pass. If the SYN exists with an ACK, in other words, in this response, I'm going to allow it to pass. It sounds kind of dangerous, doesn't it? Because how do I know that that original SYN packet went out from my protected side? I really don't. But this is what is relied upon within this filtering. If this host, let's name it host A, did not send that original SYN packet, it won't be listening for this SYN ACK. So when it receives it from host B, because we passed it through the router, it'll simply say, hey, I didn't start a conversation with you, dump that into the bit bucket, and we'll move on. So it's kind of a multi-layered security here that we're dependent on with this established command. Let me slow down and take a step back here for a second. We've already defined one operator that uses ports as part of its definition. We also have three others that we're going to define as well. So let's have a discussion on ports really quickly. Simply put, if I have two hosts, we'll use it again as A and B, they want to talk to each other, there are ports. Or maybe it'd be easier to understand these as mail slots that there's a barrier here in mail slots that pass between the two. If I want to speak to B, he has to be listening on a certain slot. Let's say, for an example, slot number 23 here is defined as telnet, which indeed it is. Whenever host A wants to telnet to host B, it has to be sending out on a particular port, and B has to be listening on port 23. And it has to pass through that mail slot on that port to get through. All right. Another example, there's a combination of port 20 and 21 used for FTP. Both of these are TCP. In other words, they're connection-oriented in nature. There are also UDP ports that are out there, some of which might be like 69, which is used for TFTP, which is Trivial File Transport Protocol. And that just means that B has to be listening on 69 if we want to communicate from A to B over that specific protocol. So keep this in mind. There are numbers. The popular numbers, or the assigned numbers, if you will, are between 1 and 1024. But there are protocols that exist on port numbers higher than that. Okay, so let's move on to the next operator. This is GT, which means greater than. So if I specify a specific port after this, let's say 53, that means we're going to filter on everything that is greater than 53, which is 54 on up to any number, okay? Here is less than. I'm going to skip log because we're very familiar with that one already. Here's less than. Again, if I assign port 53, it's anything 52 or lower as far as a port, okay? On TCP, or if we define the protocol as UDP, the same thing. The next one, not equal to. This is actually pretty cool. It saves you a lot of work. If you wanted to filter on everything except for a specific port, you could, again, assign the number 53, and the only thing that will either be allowed or denied, depending on the action we take here, is that DNS on port 53. All right, and then last we have here arrange. So we could say from 1 to 1024 and just have the established ports allowed to pass or denied, again, depending on this filtering. UDP is exactly the same as TCP, except for, because it's not connection oriented, the acknowledgement operator does not exist, and the established operator does not exist, as well as one we didn't list here, and that's the SYN operator. Again, because these are parts and pieces that are involved in this connection-oriented type of protocol that doesn't exist with UDP because it's connectionless. So I think I know what you might be thinking. I described extended access lists as being very robust and at the same time easy to configure. But I've gone through some of the protocols available and only some of their operators that are available within those protocols, and it's gotten quite extensive. The information you need to understand is extensive, but the operation of making the ACL and filtering on the ACL is pretty easy because we're limited to one command with many variations within the command. In other words, different protocols and different operators associated, along with different ways of defining the source and destination IP. Another reason I can say it's easy, besides the fact that it only has one command that you need to create the multi-line text file, is that we have the magic question mark that we always have in the iOS. In other words, if I type in access-list as it appears, 101 is the number for our access list. Let's say I opt for permit as an action, and then space question mark, I'm going to get a list of all the protocols that are available within my specific iOS. And those will vary depending on iOS. After that, if I want to list one of those, let's say TCP, hit a question mark, it tells me how I can define my source IP. Question mark after that tells me how I can define my destination IP. Once I have TCP any created space question mark, I'm going to see the operators that are involved with that specific protocol, some of which I have shown here. And that's what makes it easy, because not only does it list the operators, but it gives you information as to what they are used for or how they were used within your filtering mechanism. ICMP is the last protocol that we're going to look at in detail in this nugget as far as the operators involved in these commands. So we have access-list, the number, the action. We define ICMP as a protocol. We define a source IP, a destination IP, and now we would look at the operators involved with ICMP. Not all of them, but the most prominent. First one we have is echo. Keep in mind when we have two hosts, again with A and B, it's kind of feeling like cat in a hat now, isn't it? We can use the common tool ping to establish or know that we have connectivity between the two devices. The first packet that goes out from the source over to B is the echo packet, and what it's waiting on as a response is the echo reply, the second option we see here. So these two work together to form the ping command. Now if we wanted to, we could have a router between these two devices, and when we do, we could filter based on the echo reply only, let's say right here. And what would happen is A would send an echo to B, B would try to send the echo reply out, it would get blocked here, A would time out, and it would list this specific IP as unreachable. In other words, it's not there, right? Even though it is, because we use our access list correctly. Now this can be used very effectively to mask your network from the internet. All right. Another ICMP operator that we have available is host unreachable. Both host unreachable and network unreachable are ICMP error messages that come back for information from, let's say, a router back to A, just saying, you know what, within my route table, I don't see that that network even exists, or I don't see that that host exists when I try to establish connectivity to it. We can block those messages from coming back to the host. Again, a good way of masking our network. Most of the times this is used to mask from the internet. We also have our old friend log that's going to log to the console, and then redirects. Redirects are very interesting, and they're getting to be more commonplace. Let's say that I have two routers listed like this. One has a connection to the internet, okay, a serial connection obviously. They're both on the same subnet, and there's another device, a host on that subnet. Let's say N1 for Nugget 1. They're on that shared network. Now, Nugget 1 wants to be able to access the internet and at the same time the back-end corporate network that they have defined here, complete with routers and other subnets. How does it get to both? This is what it does. It defines its default gateway as the interface on this router here, and then lets this router do some work for it. As it sends a packet to that default gateway, the router says, look, consults its routing table and says, okay, that is on the back-end corporate network, that specific IP address. So I'm going to go ahead and forward it over to N2 and do whatever it was, the ping, the telnet, whatever action or protocol was specified, will run that to N2, and response would run back. What if, though, it wants to reach the internet? It would have a destination IP of N3 that is out here on the net. The packet would go to this router. It would consult its routing table and say, you know what, that doesn't exist on my routes that I know of on the back-end corporate network. I do have a gateway of last resort naming this router, but you know what, that's on your same local subnet. So it's going to send you an ICMP message back that says, hey, redirect that packet over here, because that's a better place to send it. You can stop that traffic from happening if for any reason you may need to. You may not use a lot of this in your network, but it's good to know it's there, and it's good to know what it does as well if it is there. The last one we have is time to live exceeded. We illustrated a ping here between A and B, right? But what if I have a host, let's say N1, that wants to understand its path over to N2, and in that path I have two routers, and it wants to identify what layer 3 devices are between N1 and N2. You're going to use a traceroute command. This is what we're familiar with. What it's going to do is send the normal echo packet out of N1 to this router, but with a little bit of a twist. It's going to have the time to live on that packet listed as 1. As soon as this router gets that packet, it's going to decrement the time to live, and it'll be at 0. Now that elicits a response from the router. It says, you know what, I can't send your packet on anymore because your time to live is 0, so I'm going to send you a message back saying time to live exceeded. That's why you get that response or that round trip time on your trace route every time that packet comes back. Next packet goes out with a time to live of 2, gets past this router to this router, 0 time to live again, and it sends that time to live exceeded back. So this is what you're blocking here. Keep in mind, though, if you're blocking that at a router, you're going to block those responses coming back from these routers, but when you get that last echo coming here and then the echo reply coming back because it's been successful, time to live didn't die out on you, then that successful ping will be shown as well. And we're going to illustrate all that in our routers and with our command prompts within the devices later on in this nugget. So far in this nugget, we've defined the extended ACL as a filtering tool that has the ability to filter on the source IP, the destination IP, as well as different protocols and operators involved in those protocols. Then we looked at the configuration, used our one command to make a multi-line text file. Now we're going to move into interface application. Simply put, we're going to take our ACLs that we've created and apply them to interfaces on our network to get the desired filtered effect. This network diagram should look pretty familiar to you. It's exactly the one we used in the standard access control list guidelines and definitions. First of all, we're going to have different companies represented. Company A, Company B, and Company C. Company A is responsible for router number 1 and the network behind it. Company B, router number 2 and the network behind it. Company C has router number 3 and the network behind it. Companies A and B are partners. Companies C and B are partners as well. So we have a relationship here, and we have a relationship here. We do not have a relationship between A and C as far as being partners and wanting to share information between their networks, okay? We simply have this connectivity because we want a redundant path. In the case that this path goes down, we want to be able to route through router 3 to get to the network behind router 2. In other words, Company A still wants to reach Company B simply through Company C's router, and the other way around. If this link was to go down, Company C wants to go through R1, Company A's router, to eventually arrive at R2 and the backend network for Company B. Let's go through a little bit of a review. If you remember, within the standard ACLs, we wanted to prevent 192.168.1.0, this network, or any host on this network, from traversing this link and getting over here to 192.168.5.0, or any host within that network, right? And we talked about placing a standard ACL here, but the problem was that it did not affect the alternate path. The same thing with placing a standard ACL here. The alternate path was still available to bypass that filter. Then we looked at placing it here. We thought, you know what, that works, but we're wasting a lot of bandwidth getting to here to just simply drop that packet. So let's try to place it here. When we did that, we found that we couldn't access any part of this network out here. And the reason was the standard ACL simply filtered based on source address. So when we defined this network as a source, it didn't matter where it was going, we couldn't reach anything because of that. But now we have a tool that uses source and destination IP together to define the filtering that's going to be done. The way we're going to do that is we're going to create a filter or an extended IP access list, and we're going to number it. This is going to be like an abbreviated form of the command 101, and we're going to opt for an action of deny. On the source IP, we're going to identify this subnet, so 192.168.1.0, with our wildcard being 0.0.0.255. And then what we're going to define, this is going to be source, as a destination is this network here. So the difference is going to be 5.0, 192.168.5.0, with the exact same wildcard mask, okay? And because we're going to define this as the source and this is the destination, and we want to block all traffic, or as much as we can with one statement, the protocol is going to be IP, okay? And then we'll simply hit enter. We won't use any of the operators. We could use log, but we won't in this instance. So we're going to come up with access-list 101 deny IP is the protocol. This is our source network. This will be the destination network. The next line is going to be where we permit, again, going for as much as we can with one shot, IP any source to any destination. The reason for that, so it can negate the deny all or the deny any that is implied at the end of this list. And we're going to place this access list right here and notice the. So let's jump on into R1 and start our configuration. As you can see, I've got myself within the configure from terminal mode. This is where I'm going to start typing in my access list. Access dash list 101, and we're going to deny based on the protocol IP. Now this is where we define our network as a source 192.168.1.0, 0.0.0.255, a destination 192.168.5.0, wildcard mask again, 255, and then we hit enter. All right, let's go for our second line, which is going to be access dash list 101. This is going to be a permit in this instance, IP, and we're going to opt for any. All right, now that we've created our list, we need to apply it to an interface. Which interface do we apply it to? Let's find out. As we had said, it's Ether0 on R1, which we're in now. So interface E0, IP access dash group 101. Now we need to determine a direction. Notice the application of this extended ACL is exactly the same command that we would use in the application of the standard ACL. The only variation is the number here, the ACL identifier. Okay, so let's determine a direction. We want to have a source of the .1 network, which is here, and a destination of .5. The only place we're going to see that on this interface on router 1 is in the inbound. Okay, outbound we would never see that. So this has to be applied inbound. All right, once we've done that, we can now test our traffic to see what effect that had on connectivity. Before we test, let me add a bit of information to our diagram here. Coming down to our slides, I have a connection out of this network, one of these links coming out, connected to a firewall out to the internet. And because that is true, later in our filtering with the extended access list, we're going to want to filter on TCP, UDP traffic, and what we're going to do is have our host exist here as 5.254. Remember in the previous nugget, we had the host existing on this side or in this network and testing in this direction. Because we want to filter based on TCP and UDP traffic, I have now located the machine that we're on now, or our host, here. So the test is going to be a matter of trying to access this network this way from network 5 to network 1, and then that return path will be blocked by our access list if it's configured correctly. We have the internet, as I stated earlier, that we can use as a destination for later testing, but for the initial test that we're establishing now, I'm going to use a node here that is .252 on the 192.168.1 subnet. So we will ping from 254 to 252 across this leg and see what we come up with as a result. All right. Let me use the up arrow, and there's my command. I use a -T at the end, so it will be constant. And this is the destination address we are pinging from this host. Here we go. We should receive a request timed out. That's because the packet is traversing the network, getting to 252, and then as 252 tries to transmit out, it's getting blocked here. Now, the only way that I can prove that to you is I'm going to leave that ping running. We're going to come down here to router number 1, bring it down a bit. And what we're going to do is use our up arrow, and we're going to add the no form to this command. So no IP access group 101 in. And then the result is the reply as soon as we say no. So once that access group is gone, we're good to go, and we're replying. So let me turn that down now and move back to our map. Now that we've successfully blocked traffic coming from company C to company A, we need to do it in the other direction and apply an access list right here that is just the opposite of the one that we established here. So let's do that. We're going to move into COM3, and here you see that I've moved into configuration from terminal mode, and I've even typed in the first command, access list 101 deny the IP address of the source, which now is going to be the .5 network because it's in company C, going to the .1 network in company A. I don't have my final 5 here, and the reason for that is I wanted you to be able to read this command, because as soon as I click in with the 5, move that up a little bit, the command shifts over to the left and you can't see the whole thing. So now my command's ready to go. That's the first leg, and then I need to establish the second. So access -list 101, and this time we're going to permit IP any. Now we need to establish it on an interface. Let's move this up. Here we go. We're going to put it on fast Ethernet 2/0. So interface fast ether 2/0, and then as we always do, IP access -group 101, again in the inbound direction, because obviously the way we're using our IP addresses. All right, now we're going to measure the effects of having that in there by pinging from the same node .254 over to .252 on 192.168.1. And we'll make that happen by using the same ping command that we used earlier. So simply up arrow on our command prompt, hit enter, and now we get destination unreachable, and you see where it's from, 192.168.5.1, which is the interface right here on router number 3, sending us back that information. Pretty cool, right? And again, the way to prove that is get on router number 3, up arrow, and use the no form of this IP access group command. As soon as we do, we get an answer. You see that there, 192.168.1.252 coming in with a good response. So far we've accomplished the blocking of IP traffic. Next we want to move into the blocking of UDP traffic. And the way we're going to do that is I have a DNS resolver set up on this host, which means whenever I want to resolve a name to an IP address, I go through this network out to the internet to a DNS server out there and ask them, hey, I've got a certain name. What's the IP address that is associated with that name? What we want to do this time is stop that DNS query, okay? Because that DNS query operates on UDP, or connectionless oriented protocol. And I'm going to put a stop to that right here with an inbound access list on R3 at FE 2/0. I've done things a little bit differently this time around. What I did was I have router 3 in waiting with the configuration already applied. The first thing I had to do was zeroize access list 101 because I had two entries in there already and I wanted to start from scratch instead of appending to the end of the list. So the no access-list 101 command did that for me. Note that I didn't have to fill out the rest of either of the two lines to make this happen. You just simply the access-list and then whatever access list ID you have available, it will zeroize. Then I put in my two new lines. The first was access list 101 deny, remember UDP this time, and the source was a host, only this host, 192.168.5.254, which is this machine here, to anybody, because we don't want to have to just cover this DNS server. I may have multiples configured. Want them all, to anybody, equals, this is our operator, equals this exact port, which is port 53. The combination of this protocol and this port together equal our DNS queries. And then our standard permit line here. We had to apply it to an interface fast Ethernet 2/0 in the inbound direction, which is the next command here. And now we're ready to perform our test. To do that, let me get to a DOS prompt. The domain name we want to use for our test is ftp.cbtnuggets.com. Now what we're going to see here is our .254 attempting to go through the internet out to a DNS server and come back with a resolution for that name to IP address. Here's the problem. Not the problem, here's the delay. When we normally send out traffic this way, like our ping command, as soon as it's blocked by this access list, we get a response back immediately that says, you know what, network unreachable, right? You don't get that with our DNS attempt, and the reason is it's UDP traffic. Remember, ICMP traffic comes back for ICMP traffic and some other traffic, but not our DNS request. It's simply going to send that packet out there. Even though it dies here, this machine is just waiting for a certain timeout value before it's going to indicate that this was not successful. And when it does get that timeout value, you're going to see this line here, unknown host, and then it gives you the name that you are trying to access. Okay, so what we want to do now is get to our router in COM3, use the no form of this same command, and then we're going to try that again, and we will access it. But there's something I want to show you before we do that. I am going to go back to my prompt here, and I'm going to ping an IP address, ping, and it's going to be 63.241.181.46. I'm getting a response from that IP address, and take note of that IP address after we issue our command here in the router. So here's the no form of that command. I'm going to come back to my DOS prompt, up arrow twice, so that I get to where I'm pinging the name. And look at my resolution. The IP address it resolved to was 63.241.181.46, which is the same IP address, let me move this up, that we were pinging just a minute ago. So we were blocking the DNS traffic, but we did not affect the ICMP traffic, and that's why we couldn't resolve the name to IP address. If you notice, as soon as you type in the ping command here, the first thing it does is give you the answer back from DNS saying that the ftp.cbtnuggets.com name corresponds to 63.241.181.46. Let's now move back to our diagram so that we can discuss our next test. Now we are going to test TCP functionality, and the way we're going to do that is we are going to have this host try to contact a web server or HTTP server out on the internet and see what we can block here at the same access point. It worked so well the last time, I'm going to try it again. I have our router, number 3, R3, ready and waiting again. What I have is no access-list 101, so I zeroized the entries we had in before. The new entries are deny, TCP this time, the same host to anybody, and this time equaling port 80, which is HTTP. That's how we access web servers. Okay, then the regular permit line, applied it to the interface, fast Ethernet 2/0, IP access group 101 in the inbound position. The way we're going to test this time is we're going to bring up an internet connection. What I did is I have my home site set to CBT Nuggets. Now it doesn't matter that I have it set to any particular URL. The fact that I'm trying to bring this up at all and it's not coming up shows me that my filter is working and that I am getting port 80 denied right here at this access point. Now what I'm going to do this time is I'm going to go ahead and go back into the router, up arrow so we can do the no form of this command. So we can get the IP access group off of that interface. And as we do that, we're going to go back and we're going to refresh this connection. And what do you see? CBT Nuggets up and running, okay? So we were able to block TCP port 80 at this access point. So far we've covered IP, UDP, and TCP. Now on to our last protocol example. We're going to use ICMP, the informational messaging protocol used with IP, for this example. What we're going to do is we're going to start here at 192.168.5.254, and we're going to trace route with the destination of the trace route being 192.168.1.252. Now remember how the trace route works. This host is first going to send out an echo packet. That echo packet is going to have a time to live of 1. Once it's decremented to 0 by the router, by rule, it has to send back an error message, an ICMP error message that says time to live has exceeded. What we're going to do is we're going to place our access list right here at Ethernet 1/0 in the inbound direction. And what we're going to see with that is the first 3 packets that go out to this router with a TTL of 1 are going to come back successfully. The next 3 packets that go out with a TTL of 2 that are going to make this router respond with the error messages are going to be blocked here, and we should see 3 asterisks. In other words, it'll look like it failed, but indeed it got all the way to the router. It only failed coming back to the host. The next 3 that are going to be sent out by the traceroute program are actually going to reach the destination, and the destination will reply with an echo reply, which will not be blocked by this access list because we're only going to be looking for packets with a time to live exceeded. ICMP type packet. So it's going to get through, and the last 3 we will see successfully run through. It's kind of interesting to note that traceroute does that. Even though it didn't get responses on the 3 packets here, it still increments the time to live up 1 notch, which will go to 3, and sends 3 more out, trying to bypass the problem router here and get to the host. And in this case, that will happen. So keep that in mind in your security when you're applying access list. If you block the TTL exceeded or time to live exceeded, you're not really going to hide this host back here because that traceroute program will continue to try and continue to increment that TTL until the point that it hopefully reaches its destination and gets the information that it wants. Not all the information, because it doesn't know the identity of this router in midstream that passed packets on, but at least it does know that host is there and it responded, and that there is one router between the last known host and the destination. Alright, so let's jump in our router. What we're going to see here, magically again, is that I've already configured this. No access-list 101, zeroize my access list. The first line I have in here is we're going to deny ICMP protocol from any host back to our specific host, 192.168.5.254 that we see here. And the only type of packet within ICMP that we're going to filter is TTL-exceeded. Then we have our standard permit IP any. We're going to place this on interface E1/0, and it's in the in direction. So let's do our test. What we have to do is bring up a command prompt, and we're going to trace route to 192.168.1.252. All right, now we see our first 3 packets came back pretty readily. In fact, less than 10 milliseconds you see there from 192.168.5.1, which is the inside interface of router number 3. So our first layer 3 hop. Okay, now we see our 3 failed packets. That's our access list taking effect, and you see those right here. And as we said, it's going to increment that TTL, and the next thing it does is it hits the destination host. It answers back with an echo reply and is very successful, in fact not blocked by our access list. There are many other operators available with ICMP in use for the extended access list, and I'm sure with practice and time you're going to be able to manipulate the traffic on your network to where it's running as clean as can be. In this nugget, we defined an extended access list as a filtering tool, and that filtering tool filters on a first hit basis versus the best fit. We also saw that with configuration, we used one command to configure a multi-line text file, and in doing so, this is our ACL. And then at the end, we had some detailed looks at different tests that tested the protocol features and functionality of our extended ACLs in a real network environment. I hope this has been informative for you, and I'd like to thank you for viewing.